All right. We're going to talk about, you can put your hands down. And actually, probably keep your hands down, because I'm going to go kind of fast. This is a lot of stuff to cover, and I probably won't have time for questions. I'm going to be talking about parallel programming, the sacred art of doing two things at the same time. My name is Daniel Higginbotham. I hail from Adzerk, North Carolina. I'm on Twitter. I have a website, braveclojure.com, which is home to a book, Clojure for the Brave and True. It also has now... That's it. Thank you very much. There's also now a directory of open source projects, so if you're looking to contribute, you can go there, and there's also a Clojure job board. I think the first and only Clojure-only job board. But to really get started here, this is some code which shows the kind of performance gains that you might be able to get from the reducers library. So if you're not familiar with the reducers library, it re-implements a lot of Clojure core functions for operating on collections like map and filter and so forth, and does it in such a way that you can get dramatically sometimes better performance with them through parallelization and the elimination of intermediate data structures or collections. So this code is just showing a very basic operation of taking a vector of 10 million numbers, incrementing them, filtering them, and then summing them. And the reducers version is 7 times faster. And this was run on a quad-core machine. You might think, oh, quad-core machine parallelized, wouldn't that be 4 times faster? Oh, no, it's 7 times faster. And so we'll see, hopefully by the end of this talk, have a better idea of where that performance comes from. This talk is really not about reducers per se. It's more about parallel programming and the concepts behind it, and I think that that will help you understand actually what the reducers library is doing. So to get there, we're going to end up at the fork-join framework. The reducers library relies on the fork-join framework in order to do its parallelization. It's a really cool thing. To understand the fork-join framework, though, we're going to start with some basics of what is parallelism, what is parallel programming, why does it matter, why should you care? Then we're going to talk about performance, because this is really all about performance. This is why we care about the reducers library, because it gets better performance. We're going to talk about some general performance strategies, and then focus specifically on data parallelism. And once we cover all of that, we'll be ready to then look at the fork-join framework, which embodies a lot of best practices for parallel programming. Cool. So let's start with some basics. Why should you care? Why do you care about parallel programming? The main reason is performance. You may have noticed in the last 10 years that the CPUs on your computers, their clock speeds have barely increased. Not at all like the previous decades where clock speeds were increasing, about doubling every 18 months or so. Right? What we have now instead is an increasing number of cores on our machines. And the reason for this, well, there are 3 main reasons for this. These 3 limitations. The first one is called the power wall. If we were to dramatically increase the clock speed of a processor, then it would actually exponentially increase the amount of time the amount of power that the processor would have to consume. It would also dramatically increase the amount of heat that it would output. So really not feasible to dramatically increase clock speeds. The next limitation here, the memory wall, the deal with that is that even if you did increase clock speeds, the memory bus isn't fast enough for the CPU to actually access your data and make use of this increased clock speed. So that is another limitation. The ILP wall sounds fancy, and so that's why I put it up there, but I'm not really going to talk about it. You can Google it. It's really not enough time. The other reason why is robustness, and this actually is kind of has more to do with distributed programming, but hopefully the ideas that you'll learn here, I think a lot of them will kind of apply to distributed programming as well. Like in this system we have here, we have the Cthulhu system, and he has many tentacles, and he has good failover there where if one tentacle is severed or something like that, he can still capture you and devour your soul and send it to the abyss, whatever, and scale. So those are the main reasons why you should care about parallel programming. I'm actually going to go back to the previous slide. One thing I forgot to mention there is also this trend is just going to continue, right, with multi-core machines, right? So in order to make best use of modern hardware and to write programs that are able to run faster without having to change anything on new hardware as it's released, you have to explicitly code for parallelism. So learning these skills, I think it's valuable to learn them, and they're only going to become more valuable in the future. All right, so that's why you should care. Now, what actually is parallelism? What's parallel programming? To explain this, I'm going to start with concurrency because I think it's just useful. It's a useful way to understand parallel programming. And so a lot of you guys are probably familiar with this example. It's a classic computer science example, the Gaga model of concurrency and parallelism. It's based on Lady Gaga's song Telephone. And in this song, Lady Gaga is at a club, and one of her suitors is blowing up her phone with texts and calls and whatnot. But she says, hey, I just want to dance, okay? And so in the lyrics, she says, I cannot text you with this drink in my hand, eh. And so this Gaga model we would say that this is a non-concurrent system. She is refusing to even contemplate managing two tasks at the same time. All she wants to do is drink. And while I can understand that, I feel like this is not a great programming system. Or computational system. So if we were to upgrade the Gaga model, the lyrics would be, I will put down this drink to text you, then put my phone away and continue drinking, eh. And so in this case, we would say it's a concurrent system because she's managing two tasks at the same time. She's not executing them both at the same time, but at least she's now handling both drinking and texting. Another wrinkle of this would be to say if she were to send a text message and just stare at her phone and wait for her suitor to respond, we would say that would be a blocking operation. She's waiting for some kind of response, right? And that's preventing her from drinking, which is terrible. And so if she were to put her phone in her pocket, right, and wait for it to buzz, then we would say that she's handling that task asynchronously. All right, so concurrent but not yet parallel. So if we were to upgrade the Gaga model or the Gaga system even further, the lyrics would be, I can text you with one hand while I use the other to drink, eh. And so this is now a parallel system. She's actually executing multiple tasks at the same time. So this is the theoretical model. We're all familiar with it from our CS 101. And so that's just like conceptually what concurrency and parallelism are. So the way that this is implemented on the JVM is with threads. And so I've talked about managing tasks, and I think of tasks as just some work you do. I think of it actually as a function call, but from the execution standpoint rather than the semantic standpoint. You don't really care about what's happening or the meaning of it. You just care about, there's some work that has to get done. And so these tasks get assigned to threads, and then threads are scheduled on processors. And then that's how the tasks get executed. So in this diagram, the square dealios are tasks. The solid line is a thread, and the dashed line is a kind of execution timeline. And then at the bottom, there's an alligator, and it's roasting a marshmallow. So this next example shows like how you could actually have a concurrent system. You'd have multiple threads, and your processor switches between the threads. That's called interleaving. The tasks are interleaved. One important thing about this is that you don't know the actual execution order of these tasks, so that can lead to, it means that the execution is going to be non-deterministic, and that causes all kinds of problems. Oh my God, no. With like race conditions and deadlock and so forth. Clojure makes it easy. I'm not going to spend time on that, but it's cool. We have great things to deal with that. So finally here, we're just looking at parallelism, how this would work with multiple cores. You have multiple threads, and then the system, your computer will try to map each thread to a core so that those tasks can be executed simultaneously. You still don't know the actual absolute execution order of these tasks. But yeah, so that's parallelism, roughly how it's implemented for reals. So that is your crash course on concurrency and parallelism. Now let's talk about performance, because that's what we really care about here. Usually when people talk about performance, they use it in a general way to refer to that thing to improve so that your program sucks less. So there are actually a few different aspects of performance. The first, which we probably care about the most, is latency, and I define it as just the amount of time it takes some task to complete at any level of granularity. So like how long it takes for some page to load, or just your database query to come back. Anyway, latency, we care about that a lot. The reason why we do parallel programming is so that these computations take less time. Throughput is the number of operations per second that your system can handle. We don't really care about that so much in this talk. Utilization, that is the degree to which some resource is active during some time period. We care about that a lot, right? So we have these multi-core systems now. We want to make the best use of them. We want to make sure that all of our cores are being used, right? That's why we're doing parallel programming. Speed up is a term that is specific to parallel programming, and that is the degree to which your algorithm will run faster on parallel hardware versus just being run serially. So you want to get a decent speed up. Like at the beginning, we saw like a seven-fold increase in the amount of time it took to do some computation. Yeah, and then finally, there's this thing no one cares about, so skip it. It's power consumption. All right, so that's kind of a brief overview of performance. And now we're just going to look at some general strategies for dealing with performance. And so the last one you can see is data parallelism, but I want to talk about a couple other ones too, just so that you can see where parallel programming fits into the broader scheme of things, the kind of programming universe, and you can have a better understanding of where reducers fit in, just in the performance universe, right? So we're going to start out with latency hiding and functional decomposition. You guys can read it. So I feel like that's the worst thing, just read slides out loud. Anyway, but I'm going to do it on this one. So latency hiding is just like a fancy word for something that you do all the time, right, with programming. It's just handling stuff asynchronously, right? You want to, some operation is blocking, you're waiting for it, you want to put it in the background and hide it, right, so that your main thread can continue. So we do this, of course, all the time in web programming, like Ajax is a thing. On our servers, right, when you're like retrieving a file, often we'll use a future or something like that to retrieve a large file so it's not blocking the main thread. So fancy word for something you do all the time. There are many real-life examples of this. It's pretty important. This comic shows a tragic example of not making use of latency hiding. And so the narrator here is saying, alone. So very alone. Nothing but my thoughts, an occasional noise, or worse. No books, no phones, not a single printed word. It was the worst 4 minutes of my life. So if he had been making use of latency hiding there, he would have had a better time. All right. So functional decomposition is when a group of environmentally conscious teenagers summons an avatar of the Earth to clean up pollution. It's also just another term for something we do a lot. It's when you split your program into logical modules and have each module run on a separate thread, right? And so on the JVM, our Java programs do this actually all the time, always, because when you start up a Java program, the garbage collector runs on a separate thread, right? So you're already doing this. But one thing about functional decomposition is that you only get a kind of constant factor speed increase, right? So if you split your system into two modules and each module is running on a separate thread, and well, okay, so you have two threads. Well, let's say you have a quad-core system, then you have two cores that are idle unless you do other things to make use of those cores, right? So you get a kind of constant factor increase. I think that core async is cool for this kind of thing. You have almost basically separate programs running, but are able to communicate within the same program. But yeah, so functional decomposition. Fancy word for something we do all the time. Data parallelism. So this is the real meat of the talk. This is what we really care about. So data parallelism is when you take some computational task and break it down into subtasks, relatively, usually homogeneous subtasks, and then execute or try to execute those subtasks in parallel. Right? So often, like the kind of basic example of this is with the map, right? You want to map over, like say, 10 million items, right? You could break it down into smaller collections of, say, 512 items. I'm just picking those numbers randomly, and then operate on those sub-collections in parallel, and then recombine the results. I feel like this was dramatically demonstrated in the movie Terminator, starring the governor of California. And so in this case, the task was eliminate humanity, right? And so this was broken down and to subtasks of just kill whoever's in front of you. And those tasks were distributed among Terminators. You could say it was a parallel reduce operation. Yeah. Yeah. All right. So okay. Okay, the fun time's over now. All right, no more laughing. So So this is where shit gets real, all right, data parallelism. All right, so now we're going to talk about some theory, the work span model. This will help you kind of reason about parallel performance in the abstract. And then we're going to spend a lot of time on implementation, right? So the implementation concerns of data parallelism are, huge. If you structure your subtasks incorrectly, if you do this incorrectly, the parallel version of your code could actually run slower than the serial version. So no one wants that. So we're going to talk about how to avoid that, right? So let's start with the work span model. Who's heard of the work span model? Just raise your hands. Oh, okay, me and like 2 other people. Cool, great, this is perfect. All right, so the work span model helps you reason about parallel performance by describing performance at 2 extremes, all right? So at one extreme, we have the amount of time it takes your algorithm to run on a single core machine, and that is the work of the system, right? So with data parallelism, we have some tasks, we break it into subtasks, right? And here, this is just some made-up example. We've split this task into 15 different subtasks, right? And we'll say that each of these subtasks takes unit time. So the work here would be 15 units of time, right? On a single core machine, it just has to do each of these individually, 15 units of time. So the other extreme is how much time it would take to execute this algorithm on a theoretical or ideal machine with infinitely many processors, right? And so that is determined by something called the critical path. And so the critical path is the longest chain of serial dependencies within your algorithm, right? So the deal with serial dependencies, you can see here some of these tasks are highlighted with gray, right? So the very bottom task depends on the task before it to be completed. Therefore, you can't parallelize that, right? So no matter how many more cores or processors you throw at this, right, that you can't make that go faster, right? So the longest chain of these tasks is called the critical path, and it determines it's more like it's like the upper limit to the amount of speed up that you can get by parallelizing your algorithm. So the work span model defines these limits, and it helps you kind of reason about what's the theoretical limit to the speed up I can get, right? So we could say the work here is 15, the span is 5, and so at most I can get maybe a 3 times increase in performance by parallelizing this, no matter how many cores I put it on, right? So we're going to look at a few examples of the work span model. So with map, the span is 1 because each application of the mapping function is independent of all other mapping applications, right? So on this ideal hardware, we could run each mapping application on a separate core and do it all in parallel. In the literature, there is an adorable term for this. It's called embarrassingly parallel, and which I just love because it's like, oh, excuse me, was I just parallel? Oh, pardon me. So that's embarrassing parallelism. Reduce is. I think we all know what reduce is, but anyway, reduce can be parallelized. This is important. There's a whole library called the reducers library, which relies on this fact. I'm not going to spend too much time on this. This diagram just shows like, hey, yeah, you run it in parallel and it runs faster. Cool. Next, we have a scan operation. So scan is also known as partial sums. It's kind of like reduce, but you keep all the intermediate results as well and put that in a new collection. So scan's interesting because it has more complicated data dependencies, right? And so this next slide kind of shows that. I'm not really going to get into the details of how scan works. The important thing that I want you guys to take away from this is that when you parallelize scan, you actually end up doing more work than in the serial version. So like on the left-hand side, we have these 7 tasks, and on the left-hand serial side, 7 tasks. On the right-hand side, there are 11 tasks, yet it runs faster. So this is kind of counterintuitive, and I think it's counter to how we think, normally when doing serial programming, you try to eliminate work, but with parallel programming, sometimes you actually do more work, but the overall task is faster. So that's kind of cool, and I think that's part of what makes parallel programming fascinating for me. Also, I forgot to mention, there's a cool paper out there, just like I think if you Google like parallel scan PDF or something like that, I don't, you'll probably get something good. Anywho, all right. So those are kind of the theoretical concerns with parallel programming. Now we're going to talk about implementation. All right, so the main deal with implementation is that you want to balance amortizing overhead, right? So reducing the amount of overhead relative to the real work that you're trying to do versus keeping your cores saturated or load balancing, right? So you might initially think, oh, I want to parallelize this algorithm. I want to parallelize map, for example, right? And so I'll assign each mapping function application to its own thread, and I'll create like 1 billion threads, and they'll all run, and this will happen instantaneously. If you thought that, you'd be very wrong, because there's a lot of overhead associated with thread creation. Also, if you create too many threads, then your system will just grind to a halt, right? So you need to manage your threads, right? On the other hand, so there are techniques for doing that, right? But if you go too far or go too extreme with those techniques, then what happens? I mean, you would say, if you take it to its further extreme, you'll say, like, well, I'll just put it all in one thread, and then it'll be serial, and I won't have parallel overhead, right? So, but that would obviously defeat the purpose, right? So you want to keep your course saturated as well. So we're going to talk about some approaches to doing this, thread management, and then also a few different approaches to decomposing your main task into subtasks. We'll cover those. All right, so let's talk about thread management. The main way that we manage threads on the JVM is with thread pools. That's a picture of a thread pool from the Lord of the Rings movie. It's like these 9 ring wraiths too. Anyway, whatever. I'm going to explain thread pools now. All right. So the deal with thread pools is that they're a layer of indirection between tasks and threads. So instead of putting a task directly on a thread, you hand your task to a thread pool, and then the thread pool manages things like creating the thread and ensuring that not too many threads are created and so forth. So thread pools, they mostly live in the Java util concurrent executors package that has really great documentation, and I think it's just fun to read. So there are a few different kinds. No, I'm serious. So there are a few different kinds of thread pools, right? There are caching thread pools, and the deal with those is that if you hand it a new task and there is no idle thread, it will create a new thread for you, but then the thread will stay around for some amount of time, like a minute or something like that, so that even when it's done with its work, if you hand this thread pool a new task, it can just go on that idle thread. It doesn't have to create a new task. Clojure's futures use that, which that code proves. No. There are also fixed-size thread pools, right? We use these often, I think, with databases. A fixed-size thread pool often just create a certain number of threads. When you create the thread pool, that way you reduce the amount of time it starts to, the warm-up time to connect to a database. But fixed-size thread pools have their uses as well. I think core async uses a fixed-size thread pool of the number of cores on your machine plus 42. Thread pools also manage queuing your tasks. So if none of the threads are idle, then it will just keep track of all the tasks that you handle it and then hand it off to the threads when they are idle. So cool. All right, so thread management. I think that's basically it. So again, here's this code. It's just, I'm not going to spend time on it, but just I think if you just go through the Clojure source code, like clojure.core namespace, and look up futures, and then just keep digging, then you'll end up with what you have here, and you can see like, oh, cool, okay. Clojure actually starts up this cache thread pool at the beginning and then uses it for futures. Pretty groovy. All right, so that's thread management. The next approach that we have to dealing with parallel programming implementation is task decomposition. So the first thing we're going to talk about here is granularity. So granularity refers to just the size of your subtask, right? And so it might not seem like it at first, but this graph shows a pretty sad state of affairs and then a happier state of affairs. The white squares are just the subtasks, the work that you want to do, right? And the greenish, or I can't tell if it actually looks green, but the colored rectangles represent the parallel overhead that you have. And so in the very first bar here, we're showing like this is some task that you want to do. It takes 16 units of time. It's 16 tasks, subtasks, that each take 1 unit of time, right? So 16 units of time total, all right? So if you were to decompose this poorly, like, for example, by using PMAP with ink, right, each subtask would then be parallelized, and all that overhead associated with parallelization, like scheduling this task, wrapping up this task for parallelization, would be incurred, and you would actually end up spending more time on the parallel version, which would suck. And so in this case, this hypothetical case, you end up taking 24 units of time versus 16 units of time with the serial case. So the bottom example shows like, okay, let's package together these subtasks and then run those packages in parallel. And that way, you amortize this overhead. The work done, the actual work that you want to do dwarfs the work taken for parallelization, and you get real performance benefits from parallelization. So like I mentioned PMAP. This often bites people. If you do PMAP with some very computationally unintensive task, right, some very simple task, then you end up taking more time with PMAP than you would serially, all right? So granularity, something to keep in mind. The next idea here we have is tiling. And so the idea with tiling, we kind of showed it in this slide, but the idea of tiling is you want to split some collection of data into these sub-collections, and you want to run your parallel operation serially on these sub-collections, and you want to take that and then parallelize that. So you can see here we have these 8 items. We split it into 2 groups, and then we operate on those 2 groups serially, but then that operation is performed in parallel, right? So that's the idea with tiling. And it probably comes actually from image processing, where they worked with literal tiles of the images. You would split these images up into groups of pixels, and then operate on those pixels serially, and then recombine the results later on. So that's tiling, and we're going to see later on the fork join framework does these things, like manages granularity and tiling and whatnot for you in a really cool way. The next idea here that we care about is parallel slack, and so you might think from what I just told you about amortizing the overhead here with granularity, you might say like, okay, I'll just split my collection into a number of sub-collections equal to the number of cores that I have, right? So if I have 4 cores, I'll just have 4 sub-collections, right? And then there'll be like very little overhead there, right? But then you can run into a problem where, let's say, one of these sub-collections, the processor gets stalled on it for whatever reason, right? Then you have all these elements in there that are bound up in the sub-collection that can't be processed when you have other processors that are free, right? So what you want to try to do here is introduce what's called parallel slack. And you do this by over-decomposing your system. You create a degree of potential parallelism that is much greater than the actual parallelism available on your machine, right? And another benefit of introducing parallel slack like this is that if you do run your parallel algorithm on newer hardware with more cores, then it's automatically able to take advantage of the newer hardware. So this is just kind of something that's really common to any kind of queuing system, and it shows up even in such diverse areas as like lean manufacturing and lean development, whatever. But anyway, parallel slack. The idea here is you want to over-decompose your system to create a lot of potential parallelism, but not go so far as to have your parallelization overhead dwarf the actual work that's being done. Cool. All right. The next idea here we have is fusion, and the deal with fusion is you want to eliminate the creation of intermediate collections, right? So if you're doing a few different operations on some collection, like mapping it, filtering it, and so forth, you don't want to create intermediate collections because that's really incidental to the actual work that you're trying to do. You want to try and just do one pass over your collection. And the reducers library actually does this. It's part of why at the beginning we saw a 7-fold increase in speed. Well, part of that was not just the parallelization, but it was because the reducers library eliminates these intermediate collections. right? And so one way that you can think about this is, this is with this code that no one would actually write, you could actually, do 3 different map operations over some collection. Well, that would be silly. Why would you do that? Instead, you would just have one mapping function, right, that processes the collection in one pass. And so the reducers library is designed in such a way that when you compose things like map and filter and whatnot, it composes those operations, map and filter, into one function that operates across the collection in a single pass. All right, so that is data parallelism. I guess I'm talking kind of fast because I'm farther than I expected to be. But now we're ready to actually look at the fork join framework, right? This is what we've all been waiting for. The fork join framework is an executor, right? So it's in the same family as Java thread pools, but it offers additional functionality. And so with the fork join framework, you hand it some kind of computational task, and you give it rules for how to decompose that task, right? And so that's where the forking comes from. The fork join framework will just decompose with reducers, it decomposes some data structure into smaller data structures and says, is this smaller data structure small enough that it meets the base case conditions? If it's not, then it just forks again. And it keeps on doing this recursively, does this recursive decomposition until it reaches some kind of base case, and then runs whatever processing you want to do on the base case. And then later, when it's done with that, it combines the results to get your final result. So that is the basic idea with the fork join framework, this recursive decomposition of a task, right, into some base case. And that's where the actual work gets done. That's where you get the most benefit from parallelization, right? And then the results of these computations are then later combined until you get some kind of final result. So the fork join framework handles thread management for you. So with fork join, I think it usually creates a number of threads equal to the number of cores on your system. It handles tiling for you. So for example, well, it can anyway. With the reducers library, you're doing some kind of collection operation, and these collection operations are fused together automatically. Also with the reducers library, it handles this tiling for you. The number 512, I mentioned that earlier, but the reducers library by default will split your data structure, like a vector or a map, into subcollections of 512 elements each, and then operate on those in parallel. So it does tiling. It also handles parallel slack for you. So the fork join framework will over-decompose your problem, right, creating a great degree of potential parallelism. If you are working on smaller data structures, like say they have 200 elements or something like that, then you can tell the reducers library to have a different base case for the number of elements that it should operate on, right? So you can continue to have this parallel slack. And the fork join framework also introduces a cool technique called work stealing. And the idea with work stealing is that if one of the threads is idle, the fork join framework will actually steal work from it and then put it on some other non-idle thread. Using this double-ended queue, it's smart, and it's able to find like the most, pull work from the kind of most complex end of this queue of tasks that you need to do. That's pretty cool. I actually don't really know all the details of how that works, but it's really neat. Cool. So that's the fork join framework, and this diagram just kind of shows what I just talked about. But so it's just meant to describe okay, when you parallelize your tasks with the fork join framework, the actual parallelized work, this is the area with the kind of purplish background. You can have multiple collection operations that are fused together. You see at the top. Then it would do some kind of reduction and then get some kind of result, and then those results are combined. Cool, and that's the fork join framework. Oh, that's really it. All right, well, let's recap. There's hardware. I actually hate recaps because I feel like the video is going up in like an hour or something. So if you just watch the video. Thank you. All right, we have time for questions. Are there any questions? No questions. Oh, yeah, go ahead. Have you done any work with GPU compute in Clojure? GPU compute? So the question was, have I done any work with GPU compute in Clojure? And the answer is no. It sounds cool, though. Yeah. Yeah, that's a great question, and I'm pretty sure that the answer is no. So when you use reducers, the functions in the reducers library, what they return back is actually an anonymous object, this reified object, which implements this reducers protocol for the reduce operation. And the return value that you get from reducer functions also kind of keep track of the initial collection that you might hand it. Right, so that behavior, I believe, is somewhat different from transducers because ultimately, reducer functions, they have to work with reduce eventually, right? Whereas transducers don't. So, does that answer your question? Cool, great. Yes.
Why do you have a single alligator with only one alligator?
Oh, the question was why did I have only one alligator? I feel like that's a very deep existential question, and we'll have to talk about it later. That's okay. Yes? Is it true that if we're going to need to use I/O, kind of reducers is not the right answer? You kind of have all your data there in the front. So the question is, if you have to do I/O, are reducers right for you? And I believe actually on the Clojure.org or .com official documentation, it says you want to actually have all your data in memory before you use the reducers library, and maybe core async or something would be more appropriate for you with when you're doing I/O. But at AdZerk, we've actually used the reducers library, and part of the parallelized task was reading a file, a fairly large file, to begin with, and I found that it still helped dramatically. So I would say just play with it and see if you get good performance increase. Yes?
Is it safe to basically ignore all of this until you need it for performance reasons? Or do you actually need to, basically can you drop in parallelism later on?
Yeah. So the question was, did I just waste the last 40 minutes of my time? And the answer is no. No. So sorry. So the real question was, do I actually have to care about reducers? Should I preemptively do reducers? Use reducers in my code? And I would say probably like nowadays, maybe it doesn't really matter, but I would say that if you are doing something that you can see this is kind of computationally intensive, then it's worthwhile to just throw reducers at it.
So it's hard to bolt it on later?
Well, no, actually, it's very easy to bolt it on later. It's, you just require the reducer's namespace, and instead of having the map function, it's r-map. So, yeah. I'm sorry, r/map. Whoops. Yeah.
Do you have any experience with the tensor library? And if so, do you know how to differ?
I don't have experience with it, so no, I don't. I forgot to mention, too, there are other libraries like Claypool, Tensor, which do this kind of parallel programming and give you more control over it. Cool. Yes, in the back.
Yeah, so you talked about the fortran framework and why it's cool. Are there situations where it's not like a better thread pool than the built-in executors or other options?
Yeah, so the question is, are there situations where the fork join framework or executor is not a better option than built-in thread pools? And absolutely, absolutely. So fork join is used specifically for this kind of recursive decomposition task, whereas, so I mentioned earlier there are caching thread pools which are used for just one-off tasks that you want to handle kind of asynchronously or in the background. So the answer is definitely the different thread pools definitely all have their uses, and it's not the case that the fork join framework would be better in all or even most cases. Yeah?
As for handling dependencies between tasks, the situations where it's not embarrassingly parallelizable, is there a way of achieving that with fork join?
Yeah. So the question is, if you don't have something, an embarrassingly parallel task, can you hand it off to the fork join framework? Oh, it looks like my time is going to, that's probably the last question. And the answer is absolutely yes. So even with the reduce function, right, the reduce function is not embarrassingly parallel because it does have these data dependencies where it depends on previous results, right? So that's a very simple example, but the fork join framework is very flexible in that you can define how to decompose, the conditions under which you decompose the task into subtasks. And I think that's it for me. Thanks, everyone.